Hey guys, I was asked to go over this question number 1 from the 2017 FRQs. This is the question about bees and their nectar source having caffeine or not. And usually when you have a graph like this, the answer key does not show you the graph. So this is why I'm making the video, to clarify that. We have our control data, which would be nectar with no caffeine, and we have our nectar with caffeine. And then we have the probability of whether the bees will revisit that source of nectar at 10 minutes and 24 hours. And then we have some standard error data built in there too. So I just printed out some graph paper and I made my grid like this. So it's helpful when you're thinking about the axes here to remember what is the independent variable and the dependent variable. Well, I'm trying to find out the effect of caffeine on the bee's memory. So caffeine is my independent variable, is what I'm trying to learn the effect of, and memory is the dependent variable. That tells me that my independent variable is always going to go on the x-axis, remember, dependent on the y. So this is going to be the memory of the bees. I would probably write out this right here, average probability of revisiting a nectar source plus or minus 2 standard errors in the mean. I'd write that all right there. Here we're going to have our caffeine group and our control group. Right, and then I'm going to make a little key here for 10 minutes and a little key for 24 hours. Now, just to point this out, you could have 10 minutes and 24 hours as your two groups, and the key should say caffeine and control. I haven't fully thought that through yet, but I think that would work. I'm going to make a scale here. Now, this is a probability, so the max I can go up to would be 1. So there's 20 little lines in this grid here, so I'm going to make this 1. I'm going to make this 0.5, and then each of these becomes 0.05. So that's 10, 15, 20. This is 0.25 here. This is 0.55, 0.6, 0.7, 65, 0.7, 0.75, right? So that's going to be that right here. Now for my caffeine group, my first piece of data at 10 minutes is 0.72. That's my control. Maybe I want to put the control on the left, but whatever. So 0.72, I'm not going to make this perfect as I would if I was actually taking this as a test. But here's my bar for the bees' probability of returning to the control. And then after 24 hours, it's down to 0.41, 0.3, 0.35, 0.4, right in here. Right, now this is my 24 hours, so I'm going to shade this one a little bit. Sorry about the phone. I was going to have this on my tripod, but I kind of wanted to go back and forth to the computer screen. So that's how that is going to look. And then caffeine is 0.83 and 0.78. Caffeine 0.8375. 83 is going to be right about here. You'll see it in a second. Be a little sloppy here. And then 0.78 is right in there. Again, I'd do this a little more carefully if I had a ruler. They might ask you to make a graph by hand, you know, on this, and then you would attach a picture. So that's what my two bars look like, or my two sets of data. I want to put in my error bars. Let's do that on one bar to make this video somewhat short. So 0.09 on my control over here at 10 minutes. So if this is 0.72, it's going up to just shy of 0.82, 0.81. So that's going to go up to there and then down to about there, right? So that's how you would do that. And that should be on each of your bars. And it tells you exactly how much to go up. Just be precise about it and think it through, right? Now, that pretty much do it for the video. I want to title this, The Effect of Caffeine on Memory in Bees. And of course, remember to put in that extra information here just to be safe. But let's see what happened. Like, what does this data show? Well, when the group has caffeine, it doesn't really affect the memory of the bees in the short term at 10 minutes. But in the long term, after a day, the bees really remember those caffeinated nectar flowers more. Right? So just to quickly go through these questions, That would be B. And then design an experiment using artificial flowers. Well, I'd obviously want a control group of artificial flowers that had nectar with no caffeine. Then I would have experimental groups of artificial flowers that had different levels of caffeine, increasing concentrations. And I would measure the number of floral visits to these artificial flowers by bees. My null hypothesis, of course, would be that caffeine has no effect on whether the bees return more often or not. And so to put that, again, I know we sort of learn null hypotheses in the context of chi-square. If you have observed and expected, another way to think this is like my expected would be the equal number of bees at all flowers, that caffeine wouldn't affect it. So I could say that my observed and my expected would be the same. So I'm just saying that context could still be there. But for this context, you do want to just simply say caffeine will have no effect on the bees' behavior. And if we have a different number of bees at different levels of caffeine, then we reject the null hypothesis. And then for D here, which says researchers found that nectar with caffeine tends to have lower sugar content. One benefit to plants and one cost to the bees. Well, the benefits to plants is two things, I suppose you could say. One is that, look, they're getting more bees to come back to the flower after 24 hours. So they should, be doing it to have more floral visits from bees, get more pollination, spread their seed around a little bit more in that case. You could also just say that they're simply saving energy because they're using sugar for other purposes. They can lower their sugar content if they add caffeine. And the last part of that is one cost of the bees. Well, they're not getting as much nectar to make their honey from if they're using caffeinated nectar. Okay, that does it.